Hello everyone, I'm Anmol Kumar Rao, a student volunteer in Unnat Bharat Abhiyan in the Institute National Law University, Odisha, under the faculty advisor Dr. Kunti Pradhan. This lecture is on the chapter Acid Bases and Salts. Now, when we talk about acids first, we will see that these are sour in taste and turn blue litmus to red. And when we move into talking about in terms of ions, it furnishes H plus ions in aqueous solution, right? And then when we talk about whether or not they release H plus ions, they release only when it dissolved in water. Now, classifying acids further on the basis of source, we see that they are inorganic and organic. For example, in inorganic, it is hydrogen chloride, right? Sorry, it is not hydrogen chloride, it is hydrochloric acid, nitric acid, carbonic acid. And then when we move on to organic acids, we see that these are acetic acid with sources in vinegar, citric acid in uh, found in lemon and orange, malic acid source is apple, right? So when we move on to the basis of ionization, we see that there are strong acids and weak acids. So strong acids, as the name suggests, are acids like HCl, that is hydrochloric acid, and then H2SO4, that is sulfuric acid. Right. So these are strong acids which ionize completely, as the name says, and weak acids ionize partially or to a lesser extent. Right. For example, acetic acid and oxalic acid. When we move on to the next one, that is on the basis of concentration, we see that there are of two types, that is concentrated acid and diluted acid. Now, here a key point to note is that concentrated acid is harmful uh, unless unless when we take dilute acid, right? Dilute acid is sort of harmful. It depends on the concentration of the dilute acid. If it's more concentrated, then it comes into concentrated acid, right? So moving on to the next one, that is properties of acid. We see here that physical properties of acid says that the it's sour in nature, sour taste in nature, turns blue litmus to red. These are electrolytes, and this is corrosive in nature. When you talk about corrosive in nature, these are acids that are harmful to the human skin, right? And they are also soluble in water. So when we see that properties of acids in chemical properties, we see that when they react with a metal, uh, right, they give salt and hydrogen. For example, we will take the example of zinc reacting with sulfuric acid plus H2SO4. We will have a salt plus hydrogen as. So we have here zinc sulfate plus hydrogen gas, right? So this is solid, this is aqueous solution, this is aqueous again, and we have a gas here, right? So when we see a reaction with metal, we get salt and hydrogen gas. So we basically get this reaction. Now when we talk about when they react with metal oxide, again it gives salt but water this time, right? For example, we will take the example of uh, calcium oxide, right? So calcium oxide, it is CaO. Just a second. It is calcium oxide is CaO. CaO plus HCl gives us salt plus water. And now to check the balance of equation, we'll just add 2 here because, yeah, this is calcium oxide, which is a metal oxide, solid. This is aqueous, this is again aqueous, and this is liquid. So this is the reaction that we get when we react metal oxides with acids, right? Now, when we talk about reaction with metal carbonate and hydrogen carbonate, we get salt, carbon dioxide, and water, right? So our next reaction is calcium carbonate, which is a metal carbonate, right? As the example here is, that is, it's a metal carbonate. So we take calcium carbonate, HCl, to give calcium chloride plus water plus carbon dioxide, right? So this fulfills the product side, right? So this is the reaction that we have. This is solid. Feel free to pause the screen and then just note down the reaction. This is aqueous, this is liquid, and this is gas, right? Now when we see what happens when metal hydrogen carbonate reacts with it, we see that it gives salt, carbon dioxide, and water again, right? So if we just add here, instead of metal carbonate, we write here metal hydrogen carbonate. Metal hydrogen carbonate. Hydrogen carbonate, we get salt, carbon dioxide plus water. For example, we have, this is our metal carbonate, metal hydrogen carbonate. This is calcium bicarbonate, right? Plus HCl, giving us CaCl2, that is calcium chloride, and water with carbon dioxide, right? So this is the reaction that we get. Now when we move on to the next slide, we have the uses of acids. That is vinegar, as I said earlier, is one of the acids that we consume in day-to-day life, which is used to preserve pickles and Chinese food. And in stomach, we see that hydrochloric acid is released, which makes the medium acidic and leads to coagulation of proteins. Right? It is used for digestion of food. Right? We have cold drinks containing carbonic acid. We have oxalic acid to remove ink or rust stains, and then we have sodium benzoate, which is used as a preservative in cold drinks and foodstuffs. Orange and amla contain ascorbic acid, which prevents scurvy. Right. Nitric acid is used in preparation of aquarellia, which is HCl and HNO3 present in the ratio of 3:1. Right. And this is used in manufacturing of dynamites and explosives, etc. Now, moving on to the bases, we see that according to Arrhenius concept, uh, it is a substance that furnishes hydroxide ions, also OH minus, in aqueous solution are called bases. So these are classified in two types, that is strong bases and weak bases. So what we look here is when they're classified in the form of strong bases and weak bases, we see that it's when they ionize completely, they are strong bases, and when they ionize partially, they are weak bases. For strong bases, we have examples of uh, sodium hydroxide. We have examples of this. This is caustic potash, and then we have etc. Right? And then when we look into the weak bases, we have magnesium hydroxide as an example. Now, when we take the reaction from strong bases, we see that NaOH underwater, like, reacts and gives Na plus and OH minus. So this is ionization completely. This is the reaction for strong bases, and for weak bases the reaction would be partial. MgOH water, add water, and then we have partial reaction, that is Mg2 plus 2OH minus. So this is partial reaction taking place. And then these bases produce only small amount of hydroxide ions, right? And when we take the examples of what are strong and weak bases, we see that sodium hydroxide is a strong base, potassium hydroxide is again a strong base, and then ammonium hydroxide is a weak base, and zinc hydroxide is a weak base, right? So moving on to the properties, we see that physical properties, these are bitter in taste, and then feel soapy to touch, and turn blue litmus to red, are electrolytes only when they conduct electricity in solution, as is what a electrolyte does. Moving on to the chemical properties, we see that when they react with a metal, they give salt and plus hydrogen gas. Right? For example, let us take the reaction of zinc again, as we took in acid. So zinc reacting with sodium hydroxide, which is aqueous, and this is solid, gives us salt plus hydrogen. So this is what happens when they react with metals. Bases reacting with metals. So this is a base here, by the way. This is a base, right? Now, when we talk about reaction with non-metallic oxides, we see we'll take the example of carbon. We take the example of slaked lime, right? So this here base reacting with non-metallic oxide gives us salt and water. For example, we have H2O. So this is a reaction that we get when non-metallic oxide is involved. Right. Now, when we move on to the next one, we will talk about reaction between acids and bases. So as we have seen in previous slide that both of them produce salt and water. And then when they react with both of them, in this reaction, acid neutralizes a base, that is reduce its effects, or vice versa. Thus, it is called neutralization reaction. So key point to note here. Now, when the complete neutralization of base by acid solution or vice versa is indicated by a sudden change in color of the indicator present in the solution. This is called the endpoint, right? So change in would color of the indicator would tell you the endpoint, and this is due to the change in pH. Now we will again discuss pH in upcoming slides. First, let's talk about common characteristics of acids and bases. Right. So both acids and bases conduct free electricity in aqueous solution due to presence of free ions, as we have seen earlier. Now, what is the effect of dilution of on an acid or base? So mixing any acid or base with water is called dilution. So it results in decrease of concentration of ions like H3O plus and OH minus. So it depends on how much uh, water you're mixing, or how much dilution are you doing, right? So this is all for like laboratory purposes. So one more point, that is this: when acids or bases added to water, the molecule dissociate to form ions. Now we talked about indicators, right? That is pH earlier. We see the easiest way to collect uh, or detect whether a solution is acidic, alkaline, or neutral is to use an indicator, right? Indicators are substances that change color or odor on adding them into a acid or an alkali solution. Now, what are natural indicators? So these are found in nature, as the name is, like litmus solution, which is a purple color dye extracted from lichen plant. Right. So when we talk about other natural ones, we have this as indicators. Now, synthetic indicators is one of another indicator which is prepared in laboratory or industry, are known as synthetic indicators like methylene blue, methyl red, phenolphthalein, which is pink in color, right, and or other synthetic indicators. Now we have olfactory indicators which give a odor, right, when in acidic or basic medium. Okay, and then it's like vanilla, onion, and clove. This is clove here. This is not clove. It's clove. Can be used as olfactory indicators. So how do we determine the strength of acid or base? We see that it all depends on the number of H plus ions or OH minus ions, right? So the larger the number of H plus ions, larger the stronger the acid is. Stronger the acid is, right? So vice versa, the lower the number of H plus ions, the weaker the acid is. Similarly, larger the number of OH minus ions produced by a base, stronger is the base. Now, how do we judge this? We judge this by indicators which shows different color at different concentrations of hydrogen ion in a solution. We see here that in acid also there is hydrogen ion present. In bases also hydrogen ion is present somewhere, right? So to measure it, we have a scale called pH scale, in which P stands for potence, meaning power, right? It's a German word which means power. Or pH in more simpler terms is power of hydrogen, right? So this is pH, and then as the scale suggests, that 0 is very acidic, 14 is alkaline, and 7 is the neutral, which is required for all living beings, right? So this is pH. And what is the importance of pH, right? So importance of pH is that animals and plants are pH sensitive. The organism can only survive in a narrow range of pH change within a pH range of 7.0 to 7.8, right? So this is important. And then when acid rain happens, the river water goes below 5.6, and it is difficult for the aquatic life. And pH in soil is important because to grow a healthy crop, right, we look for the pH range. And then we see if the pH is stable or enough to add fertilizers also, right? This is small p is always small in pH, which is important to note. Never mistake the p to be capital in pH, right? Again, here p should be smaller. Now when we see pH in our digestive system, as I told earlier, it is used for digestion of food, right? And when there is increase in acidity, that happens generally with people, so we drink milk of magnesia, which is used as a medicine, which is called antacid, right? Which neutralizes the sorry not reduces the effect, not neutralizes, right? So this is what happens pH in our digestive system. So when it increases, that is becomes acidity, like we drink milk of magnesia to control it, right? And then we see that pH change leads to tooth decay also. So we see the pH inside mouth decreases below 5.5, then it becomes acidic, as the scale suggests, right? So 5.5 is moving towards acidic, then decay of tooth enamel begins. So this is ill effect, and this is not good for our health. So this happens only when bacteria is present in the mouth, work on the leftover food particles, which ultimately produces acids, hurting, and then decay of tooth enamel happens. So we use toothpaste to prevent that from happening, right? So again, this is also used for self defense by animals and plants through chemical welfare, right? So when insects like honeybee bite you, they leave an acid on the skin, which causes pain and irritation. And to mild that pain, we use baking soda because it will give relief, and it sort of works with the acid to neutralize it. Now, when you see pH in plants, right? So, stinging hair of Nettlese injects methanoic acid, right? So, when we see that happens, we rub the leaves of dog plant to sort of cure it, right? So, pH in plants is also important to note here. Now, moving on to the next topic, that is salts, which is the last topic. We see that salts are ionic compounds which are produced after the neutralization reaction between acid and base, right? So salts are electrically neutral, as it is shown here. Neutralization between acid and base happen, then only uh, the salt is produced, right? As you saw earlier, that salt and water was produced when a metal reacted with acid, or a metal oxide reacted with base. There was salt and water produced, and then there was salt and hydrogen produced, and so on and so forth, right? So moving on, we see that sodium chloride is used to enhance the taste of the food, which is a salt, common salt, right? Now, when we see that acid reaction, an important reaction to note here is acid plus, this is a basic reaction to note. This is gives us salt plus water. Now, moving on to the family of salts. Salts having the same positive or negative radicals belonging to the same family is NaCl, or calcium chloride, which are belonging to the chloride family, right? And then we have calcium chloride and calcium sulfate belonging to the calcium family, having calcium in common. We have zinc chloride and zinc sulfate having, being in zinc family, we have zinc in common, right? So moving on to the next, we see pH value of salt, where neutral salt is almost equal to 7, and acidic salt is less than 7, basic salt is more than 7. As just look at the scale here, that when you move towards left side, it becomes acidic. Moving towards right side, it becomes alkaline, and 7 is neutral, right? Now, what are the types of salts that we have? That common salt, right? Common salt is formed by combination of hydrochloric acid and sodium hydroxide solution. It is a salt that we use in food, and it is obtained on a large scale from seawater by separating other salts from it, right? And its pH value is 7, which is making it neutral, right? So sodium chloride is also used to enhance taste of food, and then so on. There is another type of salt, that is caustic soda. But before we move on, we will talk about uses of sodium chloride, that is common salt. So it is used in food. It is also used for manufacturing sodium metal and chlorine gas by electrolysis in molten state. So these are the uses of sodium chloride, right? So when we move on to the next, that is caustic soda, chemical name sodium hydroxide, and this is chemical, so the chemical symbol, right? So this is a strong base, which is also known as caustic soda, and then this is obtained by electrolytic decomposition of sodium chloride, and in the process electrolyte decomposition of brine, and then this happens, right? So this is about caustic soda and how it is produced. So I'll just write the reaction here, that is NaCl plus we have Cl2 plus hydrogen, right? So we get these three things, that is Cl2 and NaOH, right? So NaOH is your caustic soda. This is how we get caustic soda. This is the reaction. Please note it down. So, what are the other things that we get? We get chlorine gas given at the anode and hydrogen gas given us at the cathode, right? So, the following three products, that is hydrogen, chlorine, and caustic soda, we will look into its uses. So, hydrogen is used to obtain solid fats, hydrogenation to get solid fats, and it is used to make ammonia for fertilizers, methanol, production of HCl acid. When we look here, the uses of chlorine are, it is used for sterilizing drinking water and in the production of bleaching powder, right? So next up we have uses of caustic soda, that is our NaOH. It is used for making soaps and detergents and used for making artificial textile fiber. Now, bleaching powder, this is a CSOCl2, that is calcium oxychloride, or in much more simpler terms, this is how we get it. This is the reaction. This is how the production of calcium oxychloride happens, right? Which is also known as bleaching powder. So another common name is chloride of lime, and it is solid and yellowish white in color. So uses of bleaching powder are for bleaching cotton, right, and common bleaching, and then linen in the textile industry for bleaching, right? So this is this. We see wood pulp in paper factories and for bleaching washed clothes in laundry, and as an oxidizing agent in many chemical industries, and to make drinking water free from germs. So this is the use of bleaching powder. So when we next up, we have baking soda, that is sodium bicarbonate or sodium hydrogen carbonate. Its reaction is, wait, is the reaction given here? I'll just write the reaction. Just a second. Yeah. So this is the reaction. So this is the product that we are talking about, that is sodium hydrogen carbonate or sodium bicarbonate. So it is an important product which can be obtained using byproducts of chlor, that is alkaline process. So the chemical name of baking soda is sodium hydrogen carbonate or sodium bicarbonate. So this is that, and this is the preparation method that I just talked about. This. So what are the uses of baking soda? It is used as an anti-acid, and it is used in making cakes, right? And cakes are, as you know, soft and spongy. The bread is soft and spongy, and then used in cooking as well. Baking soda is also used in toothpaste, which makes the teeth white and plaque free. And it is also used for cleaning ornaments made of silver. And sodium hydrogen carbonate gives carbon dioxide and sodium oxide on strong heating. Thus, it is used as fire extinguisher also. So when you have a question of what does fire extinguisher have, when sodium oxide and carbon dioxide have strong heating tendencies, we see that we have sodium hydrogen carbonate, right? That gives us uh, sodium oxide and carbon dioxide on strong heating. So this is the reaction that is for making baking powder. This right here. We have baking soda, right? This is baking soda. Now, what are the uses of baking soda? We talked about here, right? This is baking soda. Now, next up, we have washing soda, that is sodium carbonate or Na2CO3.10H2O. In this, we see that it is a white crystalline solid. It is solution in water in alkaline nature, and it turns red litmus to blue, right? So, and it is obtained by rehydration of anhydrous sodium carbonate. So when we add water to it, we get sodium carbonate. That is our washing soda. So what are the uses? It is used in cleaning of clothes, especially in rural areas, in the making of detergent, cake, and powder, permanent hardness of water, and is used in glass and paper industries. Next, we have plaster of Paris, which is also called calcium sulfate hemihydrate. It is obtained by heating gypsum, that is this CaSO4.2H2O at 373 Kelvin, which is our temperature. And then gypsum loses water molecules and forms plaster of Paris in this heat. And when gypsum is heated above 400 Kelvin, dead burnt plaster anhydrous CaSO4 is obtained, which does not have the property of hardening. Right? This does not have a property of hardening. So we get plaster of Paris like this. Now, important point about salt is that you just look into these slides or go back in the video and just take a screenshot and keep it with yourself. Right. So next up, this is a common slide. You can just take a screenshot and then keep it with yourself. Next, we'll talk about the water of crystallization, which is the last topic, and then we'll end the lecture here. So many salts contain water molecule and are known as hydrated salts, right? So the water molecule present in the salt is known as water of crystallization. For example, we have copper sulfate pentahydrate, which is blue color of copper sulfate, and this is due to the presence of 5 molecules of water, right? So since there is water molecule as hydrated salts, right? So when they are present in salt, it is called water of crystallization. For example, as here CuSO 4.5H2O, and then there is another one, that is ferrous sulfate, hydrated ferrous sulfate. So when it is hydrated, we write H2O. So in this we have 7H2O, right? So moving on to the next one, we have washing soda, that is Na2CO3 dot 10H2O. Wait a second. We have 10H2O. So this is our washing soda. So it has hydrated salts, or more so water of crystallization. Or simply to remember, water of crystallization is the fixed number of water molecules present in one formula, right? In unit of salt. So that is water of crystallization. And with this, we come to an end. Thank you.